Oh, hey everybody. Welcome. Happy Friday. I have a top hat attendance thing up. If you're here in the room, please do that. We're actually going to ask a couple top hat questions today. So after you answer the question, you can just leave them out because I think we're going to be doing one fairly quickly. Again, this is not for any credit anymore. This is purely for your education and my seeing where everybody's at on these particular issues. So please do the attendance thing if you are here. All right. So let me remind you, because I didn't check, and I usually check on Friday morning, but it's usually after a homework set, and there wasn't a homework set. So you probably may have forgotten also that there was a reflective writing assignment that was due today. I haven't even gone on to check to see if anybody's done it yet. In fact, let me just share my general philosophy with these reflecting writing things. If you forget to do it one week, that's okay. Do it the next week. The point is not, I don't want to do, you may get, instead of 10 points, 9 points or 8 points or something. It's okay. As long as you eventually do them, that's the point. I mean, it's better if you do them on time, but if you have forgotten to do it one week, don't let that stop you from still doing it at some point. So go back and do it. So if you haven't done it this week, take 10 minutes after class, log on, just get it done today at some point. That's fine. Okay, where were we? We were talking about fluids, static fluids. And we derived an equation in class on Wednesday for the pressure difference for a fluid element from the top of it to the bottom of it based solely on conservation of forces and forces adding to zero, basically. And you might remember that I'm closing down the attendance thing now. We got to an equation that looked like this. Basically, delta P, the change in pressure, is rho times G times delta Y, some change in height. So here's a concept question for you. Pull out your top hat devices again. The concept question is this. You have two flasks that are circular. One has a diameter that is twice the other. Flask A has a diameter that is twice the diameter of flask B. The question is, what will be the relative pressures? And it's the same fluid. Let's say it's water. What will be the relative pressures at the same height h below the surface of that fluid? Will they be equal to each other? Will PA, pressure at A, be twice pressure at B? Will the pressure at A be 4 times the pressure at B? Or will it be half or a quarter? Say at the same height for these two flasks A and B, what will the pressure difference be at that particular point? Which will be higher and by how much? This is exciting. Type a screenshot. You've got 5 choices, A through E. Oh, not putting 3. Go. Are you seeing this? You are. Oh, okay. This is a little bit different than it is in the past. That's okay. You've got 30 seconds left. There's no penalty for getting it wrong. There's no bonus for getting it right. But aside from the pat on the back that you can give yourself for being so smart to know the answer to this question. Ten seconds left. All right, let's see what we got. Survey says, interesting. A is the winner. But every single one of these got at least one vote. So that is interesting. Okay, let's think about this just in terms of the equation that we just wrote down. The change in pressure between 2 points in a fluid is dependent on three things: the density of that fluid, the acceleration due to gravity, and the difference in height between two layers in that fluid. Does it matter what the radius of the flask is, how the pressure is going to vary with height? It does not. We could make this a pipe that goes down and comes back up and goes down again and then moves over here and goes down and then over. The only thing that matters between the pressure here and the pressure here is the difference in height against the gravitational field. That is the only parameter that matters in determining the pressure difference between 2 points. They don't even have to physically be above one another or be connected. They have to be connected to one another, because that's important, because that's what the pressure influences it for. But they don't have to be physically on top of one another to be comparing them. As long as they are the same fluid, constant contained fluid element source, then this will work. So the answer is actually A. They will be exactly the same. Water will have the same pressure difference as a function of height for a very thin tube as it will for the ocean. It does not matter what the vertical extent is. The horizontal extent is the only thing that matters. Okay, good. All right. Let's talk now about buoyant forces. And particularly, I'm interested in Archimedes' principle, although I'm not going to write that down just yet, because we're going to go back to this picture, basically. So I'm interested now, again, in our, we've got some container, it's got some fluid in it, and we have, again, already defined some volume element here that we know the sum of the forces is zero on, because it's not moving. The question is, here's the better view of that. This fluid element right here. The question is, if we replace that fluid element with something else, a brick or a pocket of air or a balloon or anything, what would the sum of the forces look like then? And how would they be different? And how would it be different than if it wasn't submerged in the fluid? So, you've still got pressure forces acting on this object now that's submerged in your fluid. You've still got pressure forces pushing down from above. You've still got pressure forces pushing up from below. Those pressure forces, will they be any different than they were when we calculated them for the fluid element when it was a fluid element? Meaning the pressure from above and the pressure from below. I'm seeing one shake no and one shake yes. If you take let's take a cube of water, and we're thinking about the forces that are acting from above and below and the sides on that cube, and then replace that cube of water and replace it with a cube of wood or metal or something, are the pressure forces that volume experiences from above and below on the sides going to be different if it's a cube of wood as opposed to a cube of water? You think yes, why? Ah, yes. So you identified the thing that will be different, which is the mass, the force due to gravity of the thing that's in there will be different than it was before. But that was a separate component. The pressure from above, the pressure from below, the pressure from the sides of the water acting on that piece of wood will not be any different than it was before. The thing that will be different is the force of gravity on that thing. because the density might not be exactly the same. You're absolutely right. You are one step ahead of me. So the net upward force, let me change back to black. I'll say due to pressure. And it's not really due to pressure, right? Pressure is pushing up and down, but it's so there is a net upward force on this particular volume element, and that net upward force is due to pressure, but specifically it's due to the pressure difference between the top and the bottom. If there were same pressure everywhere, that would be a net zero force, and that wouldn't be pushing the thing anywhere at all. Because there's a net pressure difference between the top and the bottom, it's that delta P that gives you a net force in the upward direction. And that's a buoyant force. And that force is going to be the same whether that's a volume element of fluid or whether that's a volume element of something else. I'm going to say this is really delta P. Why don't you want to do that for me? The change in pressure is really what gives you that upward force. The net downward force and I'm talking about mg of the volume itself will not necessarily be the same because m won't necessarily be the same. Not necessarily. Probably not the same. Is same. I haven't really set this up in your notes. Replace fluid element with something else. Where's this video showing up? Oh well. Replace the net fluid element with something else. The net upward force is the same. The net downward force is not necessarily the same because that mass might be different. Okay, so here's Archimedes' principle. If you don't know who Archimedes was, this goes back to ancient Greece. He was a brilliant mathematician, did all sorts of experiments involving fluids and densities and things like that. He shows up a lot in history to math classes because he did so many important things in mathematics. He also did some important things in fluids. So Archimedes' principle is this: the buoyant force, which we'll call F sub B, is the net upward force that I was just talking about. This delta P force. What is that? We can write an equation for it now because we know that that has to be equal to the net downward force of a fluid element if that fluid element were the same size as our object. Because if there's a fluid element there, it would have a net zero force. So the downward force in gravity of a fluid element has to be exactly equal to the upward buoyant force of whatever volume that thing is occupying. So this is going to be the mass of the displaced fluid times G. The buoyant force is not equal to the gravitational force. It's equal to the net upward force due to that delta P, which is equal to the mass of some displaced fluid times the gravitational acceleration. It's equal to, so again, we have a brick here in our fluid, right? Let's take the brick out and replace the brick-sized hole with fluid. We know that that fluid will be buoyant, will be neutrally buoyant. It will not experience a net force up or down. So we know that the net force up on that fluid element has to be the gravitational force on that fluid element. Because if you replace that brick with fluid, it wouldn't be moving. Does that make sense? This is, I'm going to call this MF for mass of fluid. This is not the mass of the brick. This is the mass of the fluid that the brick has displaced. It's the mass of the water that would have been in the volume where the brick is if the brick weren't there. That's what I mean by MF times G. So you're right. You were saying gravitational force. I didn't not understand what you were saying. Really, the gravitational force on the fluid element that would be in the place of where that object was. Because that would be neutrally buoyant. And that, those two forces would have to cancel if that were just fluid. Okay, what is MF? Again, let's be clear about this. This is rho times V, right? Mass equals density times volume. But this is where it gets confusing. It's already confusing maybe. But because we've got two different things here. Rho is the density of what? The fluid. V is the volume of what? No, it's the volume of the object. This is where it gets strange, right? So you've got this brick. You want to know what the net upward force due to buoyancy is. It is you use the density of the fluid to make this calculation, but it's the volume of the brick that matters. That's going to give you the net upward force. So you'll usually do volume of rho F for rho fluid and volume of O for volume of object. Okay, so you can put all this together and you get the buoyant force is equal to the density of the fluid times G what do I have there and why do I have it? That should be a V. I'll put it off. I just changed this in my notes. That's got to be. And I'm going to be more specific here. I'm going to say instead of VO, I'm going to be the volume of the displaced fluid because this is going to be a more general thing to do. Really, it's the volume of the displaced fluid. We'll see what the difference is. When you have a brick that's fully submerged in your water, the volume of the brick and the volume of the displaced fluid are exactly the same. But if you had an object that were floating on top of the water and not fully submerged, it's just the part that's below the water that matters. It's not the full necessarily volume of the object that matters. Exactly. If the net upward force, the buoyant force is greater than the net downward force due to gravity on the object, that object will feel a net upward force and will rise to the top. If it's the opposite, then the net force will be down and it will sink to the bottom. But it's not going to fall at acceleration G because there are some net upward forces happening. It will slowly sink to the bottom. As well, we'll talk about what the important parameter is in a second. So this is that's the buoyant force. Density of the fluid, it's rho GV, but it's important to know which rho and it's important to know which V. It's very easy to get these wrong when you're doing these problems. Okay, so let's do an example. We've got a lake or a pool or a swimming or a cup, it doesn't really matter. And let's say we've got a Nerf ball that's half submerged in this fluid. So it's sitting at rest, in equilibrium, half submerged in the water. Again, this is a static case. We have no net forces now acting, sorry, we have lots of net forces acting on it, but they add up to zero because the Nerf ball is just sitting there in our water. So what can we say about the Nerf ball and or the water if this is the case? So in this case, so ball half submerged in water. Let me go back to black. So we know that the force of gravity on the ball must be equal to the buoyant force that that ball is experiencing. Otherwise, it would rise or fall. So we know that the force of gravity on the ball is the mass of the ball times g. We know that the fluid, the buoyant force of the ball is rho f times g times the displaced fluid, the volume of the displaced fluid. Okay, we know what the mass of the ball is. It is the density of the ball times the volume of the ball. What is the volume of the displaced fluid in terms of those parameters? Yes, in terms of VB, it would just be half VB. That's right. We could do this in terms of radius, but there's not really even reason to go to radius yet. Unless we're asked for radius, we won't even have to think about the radius, really. This is half the volume of the ball, simply because in this case, half of it is below the water and half of it is above the water. We're only displacing the fluid from half of the ball's volume. The rest of it is not displacing fluid, it's displacing air. So plug all these things in, we get rho ball, V ball times G equals density of fluid times G times 1/2 volume of the ball. And things just cancel out. The G's are gone, divide by G. Divide by the volume of the ball, it's gone. What do we get? The density of the ball is 1/2 the density of the fluid. It's only the densities that matter. If you want to know if something's going to float, it's the density of that thing relative to the thing that it's the fluid that it's in. If that object is more dense on average than the fluid, it will sink. If it's less dense on average than the fluid, it will rise. And that will even tell you how much of it is going to be above the water when it rises to the top, if it happens to be less dense than that fluid. If it's more dense than that fluid, it's going to slink to the bottom and just sit there. It's the densities that matter. And that's all that matters in this particular case. Okay, what if an object is not floating, held in the static fluid? Let's get to the place that you already got to intuitively. If an object is held in a fluid and completely submerged, there will be a net force up or down unless those densities happen to be exactly the same. That's what we call neutrally buoyant, by the way. If an object's density has exactly the same density as the fluid, then it will be neutrally buoyant, and it will just experience no net forces up or down. So the net force up is equal to the buoyant force minus the gravitational force. If you want the net force down, you just have to reverse those two. And that is equal to rho density of fluid times G times the volume of the displaced fluid minus density of the object times G times the volume of the object. If the entire object is now submerged, then V displaced fluid is equal to the volume of the object if object is completely submerged. So this becomes G times the volume of the object times the difference in the densities. Density of fluid minus the density of the object. So we got to the same thing. So if the fluid is denser than the object, let me just write this in equation form because it's a lot easier. If the density of the fluid is greater than the density of the object, then F up is positive and the object rises. And you can probably guess the other way, if the density of the fluid is greater than the density of the object. Oh wait, I did that wrong, didn't I? No, that's right. That's right. F up is negative and the object sinks. This is cool. And it leads us to this rather neat. Oh, by the way, this is the diagram for the thing we did yesterday. I meant to throw this up there. It's in your book. This is the piston thing where you press down on one side and you get a much larger force out on the other opposite side, proportional to the area. Fun. Look at this. This is a density tower. So what they did was take fluids of very different densities and they stacked them one on top of the other so that they didn't mix with one another. So you got honey on the bottom and then corn syrup and then maple syrup and then milk, dish soap, water, vegetable oil, rubbing alcohol, lamp oil. Very different densities of fluids. And then they dropped solid objects into them and see what happened, right? You can see the ping pong ball, very low density, doesn't even make it all the way submerged into the lamp oil because it's mostly air, right? A soda cap is more dense than rubbing alcohol, but less dense than vegetable oil. So it sinks down to the vegetable oil and then stops because it's feeling a network force upward from the vegetable oil. That cherry tomato drops all the way to the dish soap. A plastic die drops all the way to the maple syrup. A bolt drops all the way to the bottom. You can test the relative densities of objects and fluids by simply making a tower and dropping things into it and seeing how far it goes down. It does. It will, right? So if we didn't have the lamp oil and the rubbing alcohol on there, the pressure in the vegetable oil would be lower. But that's not what sets the relative, it's the change in pressure is all that matters. And so how far that cherry tomato sinks is unaffected by what's on top of it. In this particular case, it's only affected by where the densities change and how that works. The buoyant force at the top of the ocean is the same as the buoyant force at the bottom of the ocean because those delta Y's are the same. And assuming the densities are the same, then the buoyant force will be exactly the same, no matter where you are. It's the delta P that matters. It's not the P itself. I don't know if that was your question, but yeah. I want to make one of these someday, but who has the time? Okay, let's do another example. Okay, let's think about some other things. How much will an object weigh in a fluid? So you've got an object and you put it on a scale and it exerts some force on that scale, not in the water or in a fluid. And then you put that scale at the bottom of a swimming pool and you put that same object on it. What is the new weight? It's not going to be the same. What is the new weight of that object? Well, weight, what is weight? let's draw the picture too, because here is a scale. We've got some fluid here. There's our scale, and here's our object. So some object on a scale at the bottom of a pool. That's our thing. What is weight? It is the net force downward on an object. That's really all weight is. It's the net force down. So it's basically the negative of the buoyant force, right? This is Fg minus Fb. It's the negative of the net force up, I should say. It's not the negative of the buoyant force. It's the negative of the net force up. So this is just the same thing we did before, except with the signs reversed, right? It's Fg minus Fb. We're going to get GV naught again, but these two things are going to be reversed. It's going to be G, the object, times density of the object minus density of the fluid. This is, so what if you take away the water? There is no buoyant force. This resorts to G times V object times rho object, which is just G times the mass of the object, which is mg, which is the force you expect to be happening there. So it's basically that minus the buoyant force that it's feeling gives you the new force. And obviously, if that's negative, the thing is going to rise to the surface and it's not going to be exerting any force on the scale at all. Okay, that's another example. A hot air balloon. So here's how a hot air balloon works. You've got some contained fluid here. This is all air now we're talking about. You've got hot air inside the balloon and cool air outside the balloon. And in fact, it's open at the bottom, right? If you've ever been in a hot air balloon, they have to be open at the bottom so you can shoot fire into there to heat it up. So we know that the lift force, if we want to make this thing rise up into the air, that lift force has to be greater than the combined weight of all of the balloon and everything that's holding onto it and everything else. So that has to be the net force up. Again, that's the buoyant force minus the gravitational force. This is the density of the cold air. So the buoyant force is going to be the displaced cold air. So the density of the cold air times G times the volume of the balloon minus the density of the hot air times G times the volume of the balloon. And then you also have to subtract the mass of the balloon and anything else that happens to be there. Okay, now there's a homework problem, and I can't remember if it's this week homework or next week homework, but there's a homework problem coming up where you have to do this. And the thing that you're going to forget to do, they give you the mass of they give you the density of air outside the balloon, they give you the density of air inside the balloon, they give you the mass of the balloon and the basket and the people and everything like that, and they ask you, I don't know, to calculate some density, or I don't even remember what they calculate. It doesn't really matter. The tricky part of this problem will be to not forget that you have to include the mass of the air inside the balloon in the total mass of the balloon plus object plus basket, right? You think that it's basically a vacuum in there and that there's nothing in there, but it turns out that the density of the air, the mass of the air inside the balloon, is a non-negligible component of the mass of the whole thing that's weighting it down. So again, the total mass of the object is the mass of the balloon plus the mass of the basket plus anything that's hanging onto it plus the mass of the air inside the balloon, which has a much smaller density than the air outside the balloon, which is how you're going to be able to make this thing rise. But you can't forget to include that mass of the air inside the balloon. Okay, well, let's think about this some more. This is now beyond the scope of the homework problem next week. Let's think about right. Don't forget mass of air inside balloon. Included in this minus mass of balloon term. Okay, now this is interesting though. Interestingly, the bottom is open. So you're just going to be thinking about average densities inside and outside the balloon. But when you really think about what's actually going on, my system has run out of application memory. Oh, crap. That's not good. Let's get rid of Chrome. How about that? Sure. Should have restarted. Okay, again, so what is we're talking about this point right here. This has to be a continuous change in temperature and density, right? The temperature at this point can't be substantially different than the temperature at this point. So there has to be a pretty big gradient from the top of this balloon to the bottom of this balloon, because down here, you're basically in the cool air again, right? This is not going to be a constant temperature thing, and it's not going to be a constant density thing inside that balloon. It's going to be a pretty strong density gradient, in fact, inside of there. And the pressures have to be the same right here and right here, interestingly. So it's not the pressure in our fluid element, it was the pressure from below that was lifting this thing up. Where is the pressure now? Where is that delta P happening that is giving you the lift to make this hot air balloon rise? It's got to be at the top of the balloon, right? You've got a very low density, very hot air that's right at the top of the balloon, and you've got a lot of pressure pushing up at the top of the balloon, and you've got not a lot of pressure pressing down from the cooler air at the top of the balloon. That's where that pressure difference has to happen. And that's where all of the delta P has to be stored, at the top of that balloon. So P's are equal. So you've got a lot of pressure pushing up right here, and just a little bit. What the heck? What do we want to quit now? How about activity monitor? Sure, make that go away. Okay, and just a little bit of pressure at the top. Okay, how about mail? Sure, make that go away. Wow, I guess mail was using a lot of memory. Okay, so P's must be equal there at the bottom. P must be substantially higher at the top of the balloon. All right, fine. Terminal. What do I want? Messages. Sure, go away. I'm running out of things to quit. Okay. P must be substantially higher at the top. I'm running out of things to quit. I guess I can quit PowerPoint. I don't think I need anything in there. Okay, I'm out of things to quit now. What? Well, it'll have to come back. Maybe that will be helpful. Okay, something weird. Anyway, the P's must be substantially higher at the top of the balloon. It does. Let's just put this over to the side and see if we can ignore it and see what happens. must be substantially higher at the top of the balloon. Density must be a lot lower. This is P. Density must be much lower. Okay, so this is actually a preview of things to come. Hotter temperatures means higher pressures and lower densities. This is a preview of our next unit, which is going to be thermodynamics. Okay, in the last 10 minutes of class, I want to start a new topic. And that new topic will be fluids in motion. No, now it's messing me up every time I try to do anything. Okay, so some warnings before we go too far in this unit. We're gonna treat this very simply. There's all kinds of caveats I'm gonna put in here that are true for lots of fluids.
Uh-oh.
Oh, he's back. That's close.
Sorry, Zoomers. No idea what happened other than my computer's crashing all over the place. So I'm not sure when you actually went away, but all we're doing is doing warnings for fluid in motion. The first one was that the previous equations, some of them that we used, are no longer valid, and then we're going to keep it simple. We're only going to consider laminar flows, no turbulent eddies or things. That's really complicated, and there are still graduate theses being done about how turbulence works. So we're going to keep it simple. So there's that. These are going to be non-viscous fluids, meaning there's no internal friction. That makes it a lot harder. And we're going to talk about irrotational fluids, meaning no eddies, no little whirlpools that develop inside. Okay, great. So I've got 5 minutes left. Let's keep going. So I want to introduce a topic that or a concept that you might not have heard of before, called streamlines. So what do I mean by a streamline? A streamline follows the motion of a test particle through the fluid, or a test fluid element through the fluid. So if you were, again, this fluid's going to be moving around, a streamline is the path that a particular fluid element takes as it traverses through the path of the fluid. Okay, so follows a fluid element as it moves through all right, just as it moves. That's probably good enough. So let's think about how this might look. We've got a bunch of, let's say, field streamlines that look like this, right? So these kind of look a lot like electric field lines, right? And they behave a lot like electric field lines. How so? They cannot cross. Two streamlines cannot physically cross one another. Why is that? Why is it illegal for two streamlines to cross one another? There's a good Ghostbusters joke in here if you know Ghostbusters, crossing the streams. But if you don't know Ghostbusters, it's not going to be funny. Whoa, we haven't even talked about pressure gradients within fluids. That's a correct answer, but let's back it up even more simply than that. Go ahead. You'd basically have two particles coming from different places that are joining each other in a certain place and then diverging from that same place, which simply can't happen. So if you're going to squeeze these field lines together, that's okay, but they still can't, you can't take two particles that were over here and bring them to the same point over here. You've got some loss of fluid then, or gain of fluid then, and that just can't happen. So these field lines actually can't cross. And the velocity of a particle at any given point writing's hard, is tangent to the streamline. So I'm going to draw a bunch of velocities here now, right? At that point, it's there. At this point, it's there. At this point, it's there. At that point, it's there. Right? The instantaneous velocity of any point is tangent to those streamlines. Okay, let's consider a cross section of a pipe, because that's usually where we're seeing these fluids move through. We got a pipe, section of pipe. We pump fluid in one side, give it some pressure, it'll move through the opposite side, and now you've got some fluid moving through a pipe. So here's a pipe, cross section of a pipe, let's say, and let's make it interesting and say the pipe changes in diameter. It goes from a wide pipe to a narrow pipe. So you might have something that looks like this, and then there's sort of a neck, and then you've got a different cross-sectional area here. Cross-sectional area of this pipe is going to change. So it might have been here at one point, and now it's like this for the circular pipe as it goes from a large diameter to a small diameter. Okay, lots of interesting things now that we can talk about just in terms of how the flow rate has to be different in these two places. But that's a good conversation to start on Monday. So think about pipes and differing diameters over the weekend. Dream about it, and we'll talk about it more on Monday. Yeah.
I learned how